Using integration to find the surface area of a revolution builds on what we've done previously. So what we need to know is the arc length of a curve, which is done in part 4 of this series, and we're going to use that. So let's look at a couple of sketches here. Here we've got a curve from A to B. So let us say I'm taking this curve and I'm rotating it about the x-axis. Then I'm going to get a shape that looks a little bit like a vase, the shape I've got here. And we now want to look at the surface area of this shape. All right. Now, I'm looking at the outside surface area. I'm not looking at the end point, at the surface area of the discs at the end. We're not looking at that. We're looking at the outside surface area. So we're assuming it's hollow. If you want to close it off, those ends are going to be circles every time. So just as a rider, we're not looking at that. So just keeping that in mind. We're looking at the surface area of this revolution. So all this area we want to find. Now, the question is, how do we find it using calculus? And yet again, we're not going to be mathematically rigorous. We're simply going to get an intuitive understanding. So we're going to take this straight line and we're going to cut it into smaller portions. Now, I'm going to approximate, like we did in the previous section, rather than the curve, I'm going to look at it as segments of straight lines. Now, here we've got a very few segments, but that's just to illustrate the point. So if I look at it as 3 segments, that's going to help us to get the surface area. Now, if I look at it as more segments than that, if I start chopping it into more pieces, and you know the pattern by now, we're going to get these number of chops to tend to infinity. What we're going to do is we're going to look at the surface area of just one strip. Now, if I take one strip, now remember this is a revolution, so it goes all the way around. That strip, if I cut it open and open it up, I'm going to look at the width of that strip as the length, the arc length there. And we've got a formula for arc length. We'll come back to that one. But what is the height of that strip? Now remember, it goes around a circle, so it's the circumference of a circle. So what we get there is 2 pi times my radius. Now, for anywhere on this function, my radius is simply my y value. So that's 2 pi times my function value. And my length, well, I know how to find the length. That's the root of 1 plus the derivative in that point squared. So we're going to combine this, multiply this to find the area of that strip, add them all together. I'm not going through that procedure again, but I will show you the formula we come up with. So from A to B, if I've got a non-negative smooth function over an interval, the integral from A to B is this part times this part. Now what have we got? This is the length of that strip, 2 pi times the radius, which is the function. This is the width of that strip, which is the arc length. So that is where we get to this formula. Now, it's quite a messy formula, but if you know where it comes from, it makes it a little bit easier to understand. All right, so let's look at our first application. If we've got a surface area of the surface generated by revolving this graph around that interval. All right, let's first see what we've got. If you had to sketch it, we've got, that is a semicircle with radius 2. But I only want to revolve this part around the x-axis. Now remember, if you visualize what you get when you revolve it, you're going to get a hemisphere, like a cap. We're not going to look at the disk at the bottom. You can add that in if you want to look at the total outside surface area, but I'm just looking at the surface area of this revolution. But remember, you can always add that disk in at the bottom. It's just going to be a circle that you can add in. But for this exercise, we're only looking at the surface area of the revolution. All right. Now, if I look at a whole sphere, the surface area of a sphere is given as 4 pi times the radius squared. All right, we're going to keep this in mind. We're going to come back to this. All right. So let's look at what we've got here. We know to find the surface area, we now have a formula, but in that formula there's a lot of work that happens. So I first want to do some simplification before we plug it into the formula. My derivative is going to be minus 2x over 2 times the root of 4 minus x squared, which is just minus x over the root of 4 minus x squared. 1 plus my derivative squared is then going to be 1 plus x squared over 4 minus x squared. And that we can simplify to 4 over 4 minus x squared. We saw that in a previous example. Right, so my surface area is going to be the integral from 0 to 2 of 2 pi times my function times that length. Now that length is the square root of what I have here, 4 over 4 minus x squared dx. Now this looks like a horrible thing, but if we tidy it up a little bit, it's going to clean up quite nicely. The integral from 0 to 2 of 2 pi times the root of 4 minus x squared. Now this one can just be 2 over the root of 4 minus x squared, and things are looking much better. Those cancel out. I've got the integral from 0 to 2 of 4 pi dx, as simple as that. And that's 4 pi x between 2 and 0, which gives me 8 pi. All right, so let's compare this to what I had with the sphere. We got this surface area, so let me just redraw it. There wasn't enough space on the previous page. From 0 to 2, we got this surface area to be 8 pi. Our formula is 4 pi r squared for a whole sphere. So for that whole sphere, now my radius I see is 2, so that'll be 4 pi times 2 squared. So that's 4 times 4, so we've got 16 pi. Now when I rotate this part around the x-axis, we saw we would get half the sphere, and that makes sense. So it matches with the formula that we have for a sphere. All right, now let's go even more general. We're told the surface area of a cone with height h and radius r is given with that formula. All right, now I just want to say, if you get the formula, that formula is for a cone, and it includes the base because it's the total outside formula, outside surface area. So if I multiply that out, I get pi r squared plus pi r times the root of h squared plus r squared. Now this pi r squared, if I've got a cone, that pi r squared is the base. Our formula gives us the area of this outside, so this is the part we're looking for. So let's see if we can get that. Okay, let's put this cone on a Cartesian plane. How do I get a cone? By rotating a straight line about the x-axis. The height of the cone will then be this distance h. The radius r will be over here. So I'm simply taking that straight line and rotating it about the x-axis to get that outside area of the cone. Now yet again, remember, we're only going for this portion. We can add the disk at the end if it's a solid, but that's not our aim here. All right, so give me the equation of this straight line in terms of r and h. Well, change of y over change of x. This is simply a straight line where y is equal to that gradient r over h, x. All right, so my derivative, because we know we need that in the formula, is going to be r over h. 1 plus my derivative squared is going to be 1 plus r squared over h squared, which I can make one term, everything over h squared, and I've got h squared plus r squared. So let's go to our formula. Our formula says this area is the integral from 0 to h of 2 pi times my function. My function is r over h x times the square root of 1 plus the derivative square. So that's h squared plus r squared over h squared. You can do all of this simplification inside the integral if you want, but it gets very messy. So let's see. From 0 to h of 2 pi r over h, let me just tidy that up, times x. Here I can rewrite this as the root of h squared plus r squared over h dx, which gives me the integral from 0 to h of 2 pi r over h squared times the root of h squared plus r squared, everything times x. So now when I integrate, this whole front part is a constant, 2 pi r over h squared times the root of h squared plus r squared times a half x squared between h and 0. So that gives me 2 pi r over h squared times the root of h squared plus r squared times a half h squared. Whoa, that's a lot of h's and r's. And mine are starting to look the same. That gives me, the 2's cancel out. I've got a pi and an r, the h squares cancels out. So I've got pi r times the root of h squared plus r squared. And that is exactly where I want it to be. So that formula works, and we can confirm it with calculus. All right, so with the applications we've looked at finding volumes of solids of revolutions, we've looked at finding volumes by slicing, we've looked at arc lengths and surface areas.